Lewis structures help us to understand the physical and chemical properties of an element or of a molecule. And looking at the Lewis structure, you can also determine the shape and the angles a particular atom has within the molecule. So this is called the VSEPR model, and based on this model, you can tell the shape of the molecule. You can tell VSEPR model, and based on this VSEPR model, you can tell whether the molecule is polar or not. If a molecule is non-polar, that means it is insoluble in water. And if the molecule is polar, means it is soluble in water. And this helps us a lot when we are doing the chemical reactions. So what you have to do is you follow these rules to find the shape of the molecule. So what are these B, E, and G? I'm sorry if you heard any noise. I don't know, the TV just turned on by itself. Okay, so for example, we drew this structure for CH4, and carbon is the central atom. C is the central atom. And what is B? B is the number of atoms bonded to the central atom. And we see 4 hydrogens that are bonded to the central atom. So for CH4, B value is 4. Then what is E? E is the number of lone pairs present on the central atom. Is there any lone pair on carbon? No. So that means E will be 0. Then what is G? G is the number of groups that you get by adding B and E. So 4 plus 0 is 4. So if you have 4 atoms bonded to the central atom, no lone pairs on the central atom, 4 plus 0 is 4, then the bond angle is 109.5, shape is tetrahedral. So this is the way tetrahedral shape is. So this is the shape of CH4. Bond angles 109.5 means each of these angles is 109.5, and the VSEPR model is AB4. A means one central atom with 4 bonded atoms B4. And so if your VSEPR model is AB4, that means the molecule is nonpolar. Now, so I'm going to discuss all these on the next page, but you have the chart here. I did not put the chart on the next page, but here this is just I discussed 404, 109.5, and so this is the way it looks like. I have to draw it again. So here CH4 tetrahedral shape with all the bond angles 109.5. Let's look at the next case, NH3. This is NH3, and this was the Lewis structure of NH3. So here, how many atoms are bonded to the central atom? We are not counting the number of bonds, we are counting the number of atoms. So there are 3 hydrogens that are bonded to the central atom. Then how E stands for the number of lone pairs, but we are looking at the lone pairs on the central atom, which is 1. So 3 plus 1 is 4. If G is 4, BEG is 314, then the bond angle is either you pick approximately 109.5 or exact 107. Your homework side, homework problems, they will accept 107. So if I have to draw the structure of ammonia, I should be drawing it like this, because this is what trigonal pyramidal shape looks like, and with these bond angles as 107 degree. Now we have one central atom, nitrogen, attached to 3 same atoms hydrogens, 3 hydrogens, and there is one, E stands for lone pair, there is one lone pair on the central atom. If the VSEPR model is AB3E, then the molecule is polar. Let's take another example, H2O. We have two atoms bonded to the central atom, two lone pairs on the central atom, and it is 4. 2 plus 2 is 4. So your homework site will pick the angle 104.5, but any of these options are correct, approximately 109.5 or 105 or 104.5. And so water has, and if you have 2 to 4 combination, then the molecule has a bent shape. So now I have one central atom O bonded to two hydrogens B or 2, and then there are two lone pairs on the central atom. So the molecule, if you have AB2E2 VSEPR formula, then the molecule will be polar. Let's look at the other examples. C2H4, we drew this structure. Now in this one there are two central atoms and both of them are carbon. They are in the same environment. So pick any one. So let's say if I pick this, then how many atoms, again do not count the bonds, how many atoms are bonded to this carbon? 1, 2 and 3. 3 atoms. Are there any lone pairs on the central atom carbon? No. 3 plus 0 is 3. Same thing here in BF3. If you look, central atom bonded to 3 atoms and there is no lone pair on boron. Same thing here in H2CO. Carbon is the central atom bonded to 3 atoms, 2 hydrogens and oxygens, and there is no lone pair on carbon. So all these 3 examples are for this combination 303. And if you have 303 combination, the bond angle is 120 degree, trigonal planar, and if it is AB3, then the molecule is nonpolar. So let's look at, for example, C2H4. So that's a trigonal planar shape. So if you look carefully, it looks like a triangle. And the bond angles are 120 degree. Now can I use AB3 formula for my C2H4? No. AB3 means you have one central atom bonded to 3 same atoms. In C2H4, if you look, let's look at this carbon, it is bonded to 2 hydrogens and 1 carbon. So all 3 atoms are not same. That means I cannot tell right now whether this molecule is polar or non-polar based on AB3. So at this time I cannot say. Only thing I can say about C2H4 is bond angles are 120 degree, molecule, the shape is trigonal planar. What about BF3? BF3 trigonal planar shape. And then can I say it's AB3? Yes. Central atom bonded to 3 same atoms. That means, and if I can call it AB3, that means I can say this is nonpolar. Looking at H2CO, yes, 303 combination, 120 degree angle. And if I have to draw its shape here, then it is going to be like this. It is triangular shape. If you look, this is a kind of triangle shape, trigonal planar. Now, can I call it AB3? No, I cannot. Why? Because one central atom bonded to 3 atoms, but all the 3 atoms are not same. So I cannot say AB3, so I'm not sure about its polarity. So for H2CO, I can say yes, the bond angles are 120, the shape is trigonal planar. That's all I can say. Going to these two examples, the last one, look at HCN. So look at the central atom, how many atoms it is bonded to? 2. Bonded to 2 atoms, no lone pair on the central atom. You look at the lone pair on the central atom, not on any other element. You have to look at the central atom. So 2 plus 0 is 2. That's the same case here. Carbon is the central atom. How many atoms it is bonded to? These two oxygens. So bonded to 2 oxygens, 2 plus 0, 2. And in that case, the molecule will be linear. So here, if you look at this, HC triple bond N. So this is a linear shape with bond angle 180 degree. Now, can I call this as AB2? No. Why? Yes, it is bonded to 2 atoms, but they are not same. One is hydrogen, another one is nitrogen. So if I cannot use this VSEPR formula, I cannot say anything about polarity. But look at carbon dioxide. Here, carbon dioxide, I can say it is AB2. A, one central atom bonded to 2 atoms. So it is AB2, then it is nonpolar. So we can tell about the polarity of the molecules based on the VSEPR model, provided these bonded atoms are same. But what if the bonded atoms are not same? Then how will you tell about the bond polarity? That we do it based on the electronegativity. And what is electronegativity? It is the measure of an atom to attract the electrons towards itself. And if you need any electronegativity value in the exam, it will be provided to you. So for example, if you look at, these are the electronegativity values. Hydrogen electronegativity value is 2.1, carbon is 2.5. Carbon electronegativity value is higher than hydrogen. What does that mean? That means if you put the electrons between carbon and hydrogen, they are more towards carbon, because carbon has higher attraction for the electrons. Nitrogen is 3.0, oxygen is 3.5. But here's the thing, if the electronegativity difference is less than 0.5, then that's a negligible difference. What it means that if you put the electrons or a bond between 2 elements, then that is shared equally by both the elements, both the atoms, and we're going to call the bond as nonpolar. But if the difference is between 0.5 to 1.9, then we're going to say, okay, electrons are unequally shared and the bond is polar. So, for example, let's look at this case, because on the last slide, we were not able to tell the polarity of this molecule based on the VSEPR model. Now, hydrogen electronegativity is 2.1, carbon is 2.5. So, what's the difference between the electronegativity? 2.5 minus 2.1 is 0.4. This is also 0.4. If the electronegativity difference is less than 0.5, it's a negligible difference. That means the bond is shared equally, so it's a nonpolar bond. So, this is a nonpolar bond, this is a nonpolar bond. But look at this bond. If you look at 3.5 minus 2.5, it is 1.0. And if the difference is between 0.5 to 1.9, then the electrons are not shared equally. They are more towards the more electronegative element. That means these electrons are more towards oxygen. And another way of showing is, since the electrons are more towards the oxygen, what we do, we put the partial negative, delta negative charge on oxygen and delta positive on carbon, means the electrons are not shared equally. So if you have one polar bond present, then your molecule is polar. That means H2CO is a polar molecule. Now another one, HCN. HCN is 2.5, this bond 2.5 minus 2.1, 0.4, so it's a non-polar bond. But 2.5, 3.0 minus 2.5 is 0.5, so it lies here. That means this is a polar bond, and one polar bond means the molecule is polar. CO2, we were able to explain it on the last slide as Ab2 and non-polar, but then here's one thing. Here this difference is 3.5 minus 2.5 is 1.0. This is also 1.0. So the difference is more than 0.4. Then why this molecule is not polar then? Because here, so what's happening, oxygen being more electronegative, pulling the electrons towards itself. Same thing with the other oxygen, it is pulling the electrons towards itself. So we have two bonds, two polar bonds that are in equal strength and in opposite direction. So that means this is cancelling this effect. So their effect gets cancelled out and overall the molecule becomes nonpolar. Because carbon, these electrons are getting pulled in opposite directions with equal strength. So basically then it seems like nothing is happening. So we call the molecule as nonpolar. But for this molecule, you can also tell the molecule is nonpolar based on my last example here, because this is Ab2 case. And if it is Ab2 case, then the molecule is nonpolar.